Okay, so welcome everyone. We just heard an excellent ITC colloquium by Alison Sills. What was special about it is that common sense is not common. That was the lesson. So Alison practiced common sense and explained something that sounds very reasonable, and I highly recommend. We have a recording of every colloquium, so you can find it on YouTube. The other announcement is that among the admitted graduate students to the astronomy department, there is one that is sitting here, and we very much hope that she will continue to sit here in coming years. Her name is Abby White, and she's just next to me, a few feet away. And originally from Wellesley College, not so far away, but I guess it would be great to have her stay in the same area, the same weather, in the same beach. Okay, so today we have, as usual, four speakers. The first is Paixin Zhu from Harvard, who will speak about the new photoionization model and strong line diagnostics of the narrow line region in active galactic nuclei, being advised by Lisa Bewley, so we're very eager to hear more details. Then we'll hear from Angelo Riccardi, who is at the Black Hole Initiative quite often, he's over there, and at the ITC. He will talk about observing black hole spin with the NGEHD. And if any of you wonders how can you observe a black hole, that's because there is bright emission by the gas around it, I guess. If it was a naked black hole, you wouldn't be able to see it. So we will hear more about it. And then Daichi Hiramatsu from the CFA as well will talk about simultaneous and delayed optical limits on fast radio bursts. That's very interesting because so far they were observed only in the radio, so the way to crack the puzzle of what they are would be by finding counterparts in other wavelengths, so maybe we'll hear about that. And then Alison will speak again. She's coming from McMaster, and she will talk about subclusters and gas. Star cluster formation is messy. So we'll start with Paixin. Go ahead.
Thank you for the introduction. Hello everyone, my name is Paixin Zhu. I'm a first-year grad student here. Today, I'm going to introduce the projects I did in the past 2 years with Professor Lisa Bewley and also Dr. Ralph Sutherland when I was in Australia National University, which is about the AGN photonization model and strong light diagnostic. Oops. The first thing I want to clarify is, what is photonization model? Basically, the photonization model characterizes how the bulk of gas and dust react to an incident radiation field through photonization processing and predicts the emission light spectrum observed in these regions. Photonization models works well for the star-forming regions, which is also known as the H2 regions, and also the narrow light region of AGNs. For example, as you can see in the left figure, that both photonization models for H2 region and AGN regions can predict the observed optical light ratios quite well, that's observed by SDSS. The prediction from these models can be used to build the theoretical mentalistic diagnostic, which with observed light ratios will be used to estimate gas mentalisty. At first, my goal was to use the published AGN mentalistic diagnostic to study the galactic properties. However, as I compared the mentalistic diagnostic from different models, I found a huge discrepancy between them. As shown in the left figure, both assays are mentalistic measurements based on the observed N2O2 light ratio, which is nitrogen to oxygen to light observed in optical wavelengths. Based on this observed light ratio, and applying two different mentalistic diagnostic from different models, we found that a huge discrepancy, about 0.4 dex, between these two mentalistic measurements, which is quite a lot if you want to compare between different literatures. So, an initial question would be, what causes the difference? To answer these questions, we need to look into what is different between these two AGN models. We post an example in the table comparing the AGN model from Castro 17, a literature, and the other literature, Thomas 18. They are basically different in 5 factors. The first is AGN ionizing spectrum, which also known as the AGN radiation field. And the second one is the abundance set. There's also difference in properties of the dust, where one model uses dust-free assumption and the other include dust. There's also difference in density structure, which one uses constant density structure and the other one uses constant pressure structure. And finally, the difference in photon emission code used to calculate the model. One is cloudy and the other is mapping. So, which one of these factors plays the most important role? To answer these questions, we start by reproducing one of the model, Castro 17, as shown in this figure, and then change the factors one by one to see which plays the most important role. First, we compare the photon emission code, which is mapping and cloudy. We use exactly the same settings on the other OR factors and just compare using the models using different photon emission code. As we can see on the right figure, that the prediction from these two models are basically similar. And also, they are all lying far away from those observed Seyfert galaxies, which should lie in the upper right corner of these optical diagrams. So it means that these models need to be improved if you want the model to be covered or predict the majority of the AGNs. Then, by switching the comparison to density structure and compare between constant density structure and constant pressure structure, we still don't see much change in these models, meaning that further improvement is required. Next, when we start to include dust, things become much different. As you can see in the figure, considering the dust depletions effect actually move the AGN models towards the upper right corner, which is where is exactly the locations of Seyfert galaxies on this diagram. Therefore, we suggest that dust depletion should be included or considered when we're building the AGN model. Then, when it comes to the abundance set, the situation becomes more complicated. The abundance set contains the information about the relative abundance of different elements and also their scaling relations versus the total mentalistic. Therefore, we could expect that different elements to respond differently towards the change in abundance set. For example, in the left figure, when the models use uniform abundance set, which is shown in red-green, predicts higher nitrogen to H alpha light ratio. It also predicts lower sulfur to H alpha light ratios. And the other thing is that the variation in the nitrogen scaling relations also further increase the complexity. The nitrogen increments are believed to have 2 arrangings. One from core class supernova, contributing to the primary enrichment, and the other one from intermediate mass stars and AGB stars dominate the secondary enrichment. At what mentalistic the secondary enrichment start to dominate can be varied. It really depends on the star formation history of these galaxies. So we can expect that the nitrogen scaling relation would intrinsically different between different types of galaxies. And also we can see from the comparison of these two nitrogen scaling relations that the upper one can predict 0.5 dex higher nitrogen abundance than the lower one at the high mentalistic end. So that would result in the big difference in our AGN models. Based on the above comparisons, we recommend this setting, which is colored in purple and blue. We recommend these settings for AGN models. But still, we can see from our recommended AGN model, when they compare to the optical observation, there are still some fractions here, okay? Some fraction of the Seyfert galaxies that are not predicted by the recommended model. So what is missing? Recorded in the first beginning, I mentioned that those two models also different in the AGN energy spectrum. So let's see how the AGN energy spectrum affects the model. We select 3 typical AGN energy spectrum shown in this plot. They basically different in the peak energies of the big blue bump component, which is the left one, also known as the thermal component. So we can see by changing or increasing the peak energy of this big blue bump component, the AGN model from top to down to bottoms are actually moving toward the upper right corner and finally covers all those observed Seyfert galaxies in SDSS dataset. So here we conclude that the ionizing spectrum is very important. That's not the final things. Also, there will be some effects from gas pressure. By changing the gas pressure, or some people will change the density of the gas based on whether you're choosing constant density model or constant pressure model. By changing the pressure of the gas, you can also affect the AGN model and move the AGN model around on the optical diagnostic diagrams. So, to sum up, a brief sum up for now, we make recommendations on AGN model setting based on our one-by-one comparisons. And based on the recommended AGN model, we also find that not only mentalistic and ionization parameter can change the emission light ratio, but also gas pressure and AGN ionizing spectrum. There are discrepancy between these 4 parameters. And to get reliable mentalistic measurements, we need to account for this degeneracy. Luckily, we can disentangle this degeneracy by using specific light ratio that are exclusively sensitive to one of these parameters. For example, here I show the diagnostic, the light ratio that are exclusively sensitive to the gas pressure, which are basically the light ratios are not sensitive to the other 3 parameters. If our observation have this light ratio, then we could use this diagnostic to interpret what's the gas pressure of this region. And also, we have the diagnostic for epochs, although it's less than the previous one, but still we have some we can work. For example, the helium-2 H beta in optical wavelengths. And of course, we have diagnostic for ionization parameters. As we see here, our diagnostic covers from optical to UV and also infrared. And finally, the mentalistic diagnostic for AGNs. Combining these 4 diagnostic for the 4 parameters, we'll finally be able to get a reliable measurements on the mentalistic on the AGN regions, and also the mentalistic diagnostic in infrared band. So I will leave my summary here. Questions are welcome. Thanks for listening.
Narrow-line emission region are thought to be gas clouds in the host galaxy far away from the AGN, because the broad-line region is close to the AGN. The narrow line is coming from the motion dynamics within the host galaxy.
Yeah.
So if these are, for example, molecular clouds or some gas clouds, you would expect some star formation in them.
Yeah.
Is it clear that the stuff that the UV emitted by stars is negligible inside the cloud compared to the AGN?
Yeah, those are interesting questions. Actually, that's also one of our future work. So it's also, like as you just said, it's known that the star formation could be mixed with all those AGN excitation, right? And now with our model, we are only predicting those emission light coming from AGN excitation. So there's also need to be models, for example, H2 model, to account for the excitation coming from the OB stars. So one thing we can solve this mixing is to find a way to separate the excitation from different excitation mechanisms, so we can correctly account for the best properties in these regions. That's one thing we are not neglecting them. We are just, we need further step for that.
Okay, the ionizing flux, the ionizing spectrum actually depends on the black hole mass, because normally if you go to lower black hole masses, like 10 to the 5 IMBH, they're supposed to be hotter. So the accretion disk itself becomes important because it moves to like 0.1 keV. So according to your model, it should move the source to the top right in the diagram. However, from observations, most IMBHs are actually closer to the transitional region. So how could you explain this?
Okay, so as for the effect of AGN and the spectrum, we only account for, or we basically are fixing all those parameters and only shift the hardness of the thermal component. It really depends on, and we also show that shifting, basically just shifting the energy peaks of the thermal components will result in the upper right corners movements on the AGN models. But it's not always the case. I mean, if you also change other parameter, the AGN model can also, the movement of the AGN model can also switch position. And the good way to answer your question would be if we can have the AGN energy spectrum and then put into this model to see how it exactly moves. Okay.
Yeah, please go ahead.
Yeah, and can you please go back to the previous slide? Say now say your agnostics are different. Can we have any sense of data error bars? If you put them, are we able to see that they are, be able to recognize different models, or they will be far fitter into the error bars?
Yeah, you mean the comparison between different models?
Yeah.
Yeah, that's one of our work that are still being done. I have some comparison between the different models in the optical wavelengths, but not extended to infrared. And also when you're comparing, when you're comparing between the observations, you need to account for the errors in observations. Also to see whether it can give a reasonable prediction from this diagnostic.
Thanks again.
Thank you.
All right, can you hear me okay? All right. My name is Angelo Ricarte. I'm a postdoc at the BHI, although I spend half my time here in the ITC halls. I think the last time I gave a talk in this format, I said something about galaxies. And since then, as a postdoc, I've become very gripped in the Event Horizon Telescope collaboration, where I'm spending a lot of time with theoretical interpretation of our images of supermassive black holes. So as you may know, we're now at the point where we have two images of supermassive black holes resolved on event horizon scales. One of M87 at the center of the Virgo cluster, and one of Sagittarius A star at the center of our own galaxy. Despite the several orders of magnitude difference in mass scale, these images look very similar. And so far we only have linear polarization incorporated in the image for M87, where you see this nice twisty pattern of linear polarization whirling around the black hole in this way. That's something that'll be very important later. And to learn things from these images, we generally make hundreds of thousands of images from GRMHD simulations, that is general relativistic magnetohydrodynamics, and we've been focused mainly on these three parameters. First being the magnetization, the strength of the magnetic field relative to, say, the gas pressure, and how much this dominates the dynamics. So far, especially based on the linear polarization, stronger magnetic fields are favored. And these two cases that we often compare and contrast have my two favorite acronyms in all of astronomy: a magnetically arrested disk, or a MAD, versus standard and normal evolution, or a SANE. Unfortunately, it seems like MAD is the standard, which can be annoying moving forward, but it's often difficult to describe weird behavior in a MAD, which is already mad. Anyway, The sanes have a weaker and scrambled linear polarization, which allows us to rule that out. Then there's the electron temperature. The reason this is free parameter is because the mean free path is so large that the ions and electrons can have different temperatures. The electrons cool more efficiently, the ions can get heated more efficiently. And it turns out that our models also favor large ion to electron temperature ratios. In fact, up to 2 orders of magnitude sometimes. Again, models with hotter electrons are producing too much linear polarization. And then there's the spin. As someone from a galactic and cosmological background, I was always most interested in this, and a little sad that EHT tends to make the weakest statements about the spin. We don't think it's 0 for these sources, or at least for M87, just because these models don't produce significant jets. You can look at our passing model histograms and see that there are some preferences, but these are pretty indirect and not too well understood, and so we haven't made very strong statements about this. So I've been very interested in the past few years to understand how spin gets imprinted onto images that are currently accessible to EHT, and in the future, the next generation Event Horizon Telescope, or NGEHT. The cleanest way that spin is imprinted onto images is in the photon ring. And in this simulation of this movie of a GRMHD simulation, what I mean is this nice, almost static circular feature. This is made of, this is the lensed image of the accretion flow from light that's making some orbits around the black hole on the way to us. It's actually pretty easy for theorists to compute what this photon ring should look like as a function of spin and inclination, but unfortunately, it's pretty hard to access. For one, it's extremely thin, meaning that you need a very high angular resolution, and it's also really faint, usually 10%-ish or less of the total flux. Even if you were able to access it, the signal with spin is pretty weak as well, especially for pretty pole-on viewing angles, as is shown here. Even increasing from spin of 0 to 0.998, there's just a small decrease in the radius, which is hard to constrain. And so I've been most interested in direct signatures that are encoded in the plasma that we're observing right now, trying to take advantage of the first part of this famous John Wheeler quote that space-time tells matter how to move. Around a supermassive black hole, there is an ergosphere, a region where the matter is forced to co-rotate with the black hole spin axis. And so you might imagine that this has important effects on the dynamics of the inflowing gas. The problem is, compared to photon rings, that now MHD forces are also important. Fortunately, I'll show you in these upcoming slides that there's still information here that we can access. Linear polarization is the most important observable for this kind of business, because we're observing synchrotron emission, and for this kind of radiation, linear polarization is really high, and the linear polarization ticks at emission are oriented perpendicular to the local magnetic field projected onto the sky, until other things might happen to it, like Faraday rotation, which I won't really get into today. In a very useful paper led by Daniel Palumbo, sitting here in the audience, they showed that these MADs exhibited more twisty linear polarization patterns than sanes, most clearly shown in this blurred version, where you have a nice pinwheel here, and whereas the sane is more radial. They also point out a signature with spin, where it seems like the pitch angle changes. And recently, last year, we took a deep dive into that signal in a project led by Razi Yamami, who's also sitting here in front of me. Here you're looking at time average GRMHD simulations, where we have different spins here, from minus 0.94 to plus 0.94, where a minus sign is encoding a retrograde flow, where the disk is angular momentum is anti-aligned with respect to the black hole. And what you'll notice is that if you look at the pattern of these ticks, you have more radial patterns for the higher spins, and more azimuthal patterns for spin 0. In this paper, what Razi figured out is that this is really due to the underlying magnetic field geometry, as opposed to some less fundamental effect like differences in Faraday rotation, where if you rotate this 90 degrees to get from linear polarization to magnetic field, you have more wrapped up azimuthal fields for the higher values of spin. But is this the most important effect and something that appears in individual snapshots? This is something that I asked an undergraduate working with me and Ramesh, Richard Chu, a very skilled undergraduate who has made this, in fact, his second first author paper before graduating from here at Harvard. And for this project, he generated over 500,000 simulated images, no small task. And from this, we calculated various different important image features, including things like the total image asymmetry, various polarization fractions, and the morphology. And he trained a random forest machine learning model on this big table of data in order to try and infer properties such as spin, and in fact, even more parameters. If you're interested, this paper is up on the archive, and we have just responded to a favorable referee report. After churning everything through this machinery, this is how well we think we can do. So what you're looking at here are predictions from the model, where he's trained on 80% of the snapshots, and then tested the model on the remaining 20%. Different colors are different spins. These are the distributions of predicted spin. And we've given the model increasing amounts of observation to kind of figure out which observations are most important and project where we're going in the future. Pre-EHT, if all you have is spatially unresolved information, you really can't say anything. This is only total flux and the net polarization fractions. If you have a resolved image but no polarimetry, there's a hint of a signal. This is coming from the overall asymmetry, which is stronger for higher values of spin due to Doppler boosting. But once you add the resolved polarimetry, suddenly these distributions start to peak around their correct values. What's important is this pitch angle of those linear polarization ticks that you saw earlier. And so we're here. In the future, because these things are time variable, observing multiple times will enable even better predictions. And of course, we put in the real numbers for M87. Something interesting that'll matter later is that the model prefers a retrograde spin for M87. In the future, we're not only going to be repeating the same observations over and over, but the observations are going to get better. We're developing the next generation Event Horizon Telescope, or NGEHT, where the idea is to add more stations around the world and improve the technology everywhere in order to access movies with a much improved dynamic range. That movie on the bottom here is just raw GRMHD here, and then simulated image reconstruction with the Phase 1 NGEHT on the right, which looks very similar. And we're hoping to simultaneously image the jet and the accretion flow. This has prompted theorists like myself to ask, if we could see more detail, can we make even better statements about things like spin? Here you're looking at two GRMHD simulations, and I think if you just watch this for long enough, you can tell that there's a significant difference in spin, where the one on the left is a retrograde, the one on the right is a prograde. The reason I can tell is that as these inflowing streams are coming in, you can see in the retrograde the effect of frame dragging, that they have to turn around since they have to co-rotate with the black hole at small enough radius. So in general, this leads to S-shaped streams in a resolved image of a retrograde system. And this is something that we discuss in this AppJ letter recently. This is a very favorable case where you have very prominent and inflowing streams. Now, the difficulty in observing something like this is that you need very high dynamic range as well as spatial resolution. These things are very thin. Fortunately, there's also a complementary signature in linear polarization as well. Because the magnetic field is flux frozen into the plasma, the magnetic field geometry encodes the dynamics of the inflowing streams as well. And this is true even potentially in a time average. You're looking at two time averaged images here. We have a prograde MAD and a retrograde MAD. And we have this parameter called argument of beta 2, which is telling you the degree and direction of the twistiness of these ticks. And what you see in this retrograde is a change in handedness corresponding exactly with that change in angular velocity that must happen in a retrograde as well. I'll just mention that we also did simulated image reconstructions. It's a challenging but possible measurement with phase 1 NGEHT. And then here we went crazy and added 6 satellites in geosynchronous orbit to improve the spatial resolution to boldly look into the future, where then you can even see individual tiny streams potentially turning around. So in conclusion, black hole spin is imprinted onto the resolved polarimetric images, and a picture is emerging where spin is affecting the flow dynamics change the magnetic field geometry, and that gets imprinted onto the polarization signal. One thing to point out is that while there exist spin measurements of AGN at high Eddington rates from X-ray reflection spectroscopy, spins obtained by the NGEHT would probe a very different sample, those black holes with very high masses and low Eddington rates. And so that could tell us something different about cosmic assembly of these black holes. In the future, we're hoping to infer on average in the order of 30 black hole spins from polarization with the NGEHT. So I think the future is bright for spin with resolved EHT and NGEHT images. Happy to take questions.
Angelo, I must be missing something really important here, because the innermost stable circular orbit is very sensitive to spin. It goes all the way in the extreme spin case, GM over C squared, whereas in the Schwarzschild case, it's 2, and then, 6, and then in the retrograde, it's even bigger.
Yes.
So my question is, you didn't use the spectrum, but the innermost stable orbit dictates where the dissipation occurs, and the spectrum might show a signal. Did you include the spectrum in the AI algorithm or whatever?
We did not. So one thing to point out is that in these thick accretion disks, we actually don't see an obvious signature of the ISCO. The accretion flow continues inward toward the horizon. That said, there are differences in... Sorry?
The horizon itself is different.
And we do use spectral information in the Sajay Star paper of the EHT collaboration. We didn't include that in the machine learning, and there's all kinds of information we actually left on the table that could potentially be interesting.
You're saying the horizon shrinking by a factor of 2 does not make a difference for the spectrum, even though it's shrinking by a factor.
It does. Yeah.
It does?
So yeah.
I see.
Yeah. Those larger spins have a higher temperature, for example.
So you don't include that in the analysis so far?
It was included in the EHT collaboration paper, not this particular project that I was talking about earlier.
Okay. Other questions? Well, good luck with the future data. We very much look forward to seeing those.
All right, cool. Can you hear me well? All right. So I'm going to get started. Yeah, so hello everyone. I'm Daichi Shiramatsu, a postdoc in the optical and infrared division. I mainly work on like explosive transients like supernovae, but today I'm just gonna, talk about the fast radio bursts. So especially like, what we can do with the optical observations of these fast radio bursts. By the way, I'm in P317, so if you have anything to chat, just come in. So I had to start with what, fast radio bursts are. I mean, it's kind of obvious from the name. They are fast and observed in radio bands. So here, this plot shows the luminosity on the y-axis, and then the transient duration in the x-axis, which is like, in what frequency they are observed, and then their duration. So they are typically observed in the gigahertz frequency, and then the typical duration is milliseconds. So you see like, these sources. So those are the first radio bursts. So they are brighter than the galactic sources, like pulsars or, crabs. And then, so this device left free that, anything above this luminosity is likely extragalactic, while anything below here is galactic. So one source to note is this SGR 1935 plus 2154. It's a telephone number, but it's a galactic magnetar that shows some FRB-like emissions in 2020. So it's a really interesting object that might be a counterpart to the first radio burst. And so those are the first radio bursts. So they could be either repeating or non-repeating. We have these two populations, and then they are bright millisecond duration pulses at the gigahertz frequency. And what to note is that we don't really know the physical origins of these first radio bursts. But one thing to note is that you see the line here. So these shows the brightness temperature. So they show like extremely high brightness temperature, and then the really short duration. So this likely points towards to like some compact object, maybe a highly magnetized compact object like magnetars, but could be aliens or anything essentially. So just to illustrate this point, there is a wiki page of a living theory catalog for fast radio bursts. So you see a lot of like theoretical predictions on what the progenitors or what the mechanism could be. So it ranges from like neutron stars, black holes, or even to like asteroids interacting with the neutron stars. So this is what we are talking about. But then what's interesting here to me is that some of them predict some multi-wavelengths emission. Could be like, gamma rays, X-rays, or even to optical. So by doing multi-wavelengths follow-up of these FRBs, we may be able to test these theories. And so this is kind of similar to the early days of like, GRB research, where the significant advance came from the optical counterpart identification for these, for those GRBs. So what would you expect for the, FRB transient multi-wavelength emission? So one scenario could be so-called synchrotron maser model. So here you have a compact object, so likely a magnetar, that ejects a plasma, ultra-relativistic plasma with the flare energy E, and then that interacts with the surrounding medium, which is likely ejected in the previous flare. And this shock interaction creates this synchrotron maser emission that we observed as FRB. But this shock also heats up the electrons, so they might produce synchrotron emission, which starts from gamma rays, X-rays, or maybe even to optical. So these are some multi-wavelengths, emission that you'd expect from this particular model. And then, so this flare energy is important, and then also this external density is important. So depending on what kind of density distribution you have here, what how high the density is, that really affects the emission. So for the case of this SGR 1935-2154, so it's a FRB-like emission seen in the galactic magnetar. There has been simultaneous radio and X-ray observation, X-ray detections. So this remains to be the only non-radio transit emission observed to date. So, and then if you try to do this for extragalactic FRBs, the X-ray sensitivity from the current satellites are not deep enough, so you don't really expect to observe these in X-rays. And then for the case of this synchrotron maser model, this is what you'd expect from the, let's say, optical luminosity in the R band. So this is with the fixed external density and then color-coded by the flare energy. So density is fixed, and then we are just changing the flare energy here. And then depending on the energy, if it's high, it shows a really bright optical light curve that extends even up to 1,000 seconds or so. So this, you might expect really long duration transients. By saying long, I mean up to 1,000 seconds or so transients for this particular model. And then if you fix the, flare energy and then change the external energy, you see different behavior in the light curves. So, okay, if this is the case, maybe we can do something with the optical. And so now the good news is there have been quite a few well-localized fast radio bursts now. So they have host galaxy identifications. Their localization from the radio observation is good enough to 2 arc seconds. So we know where to point our telescope. And then CHIME is routinely observing these FRBs. And then if CHIME detects anything new, they make these real-time alerts. So we can, react to these real-time alerts using some CFA facilities like, Kepler CAM on the 1.2 meter telescope at the WIP observatory. And then if there's anything particularly interesting, we can also trigger MMT. So we have an ongoing program to follow up these FRBs. And then we can also combine this data set with any data from the public transient survey like ZKF and Atlas. So by doing this, we made the largest compilation of optical limits. So combining our observations, public survey, literature. So there's just a lot of data points, but I just want to say this is the luminosity limit in the G band, Atlas C band, R band, Atlas O band, I band, and Z band. And then the x-axis is the time before radio burst. And then these right panels are showing time after burst. But as I said, there's a lot of points. It's hard to see. So I'm just going to focus on this one particular FRB, which was discovered in the September of last year. So this was localized to this host galaxy. And then DSA stands for Deep Synoptic Array. So they localize this FRB within this region, enclosed by the magenta circle. And then, so this galaxy is at 344 megaparsecs, which is relatively close for extragalactic FRBs. And then this FRB is crazy active. In the highest phase, we observe people estimated there have been 100 bursts per hour. So this has been really insanely active. And then this particular image was taken by our Kepler CAM. And then this reference comes from Punsters, and then this is a different image. So this image was taken when the first radio burst actually happened during the exposure. So this is a simultaneous observations in optical, and then we didn't see anything. So, and then we got 13 simultaneous observations in optical total, and then it's shown here. But what to highlight is that, this is in the luminosity range of 10 to 40, maybe 10 to 41 to 10 to 42 arcs per second. And then compared to previous simultaneous observations done by fast readout cameras, this is at 10 to 48 arcs per second or so. So these limits are actually at least a few orders of magnitude deeper than the previous limits. So, and then there's one exposure here done by Binospec, which was started 0.4 seconds after the radio burst. So that was close, but then we don't know the exact, there's some uncertainty in the shutter opening timestamps for the Binospec. So this could have been indeed simultaneous, but it's within the uncertainty. But as I said, these our observations using Kepler CAM and Binospec for this particular FRB provided the deepest simultaneous limits for extragalactic FRBs to date. So what we can do with these limits is to compare with the models. So here I show you can define effective optical flux limit. So that is your integrated flux limit normalized by the exposure time divided by the duration of the fast optical transients you'd expect from like some inverse Compton scattering mechanisms on the pulsar magnet sphere, pulsar in the supernova nebula, supernova remnant, or maybe maser outflow. And then you can normalize that by what you observe in the radio from the first radio burst. And then these lines shows the our limits for this particular FRB, and then these boxes show some expected parameter space from these models. So here, for the first time for any extragalactic FRB, we are actually getting into the model parameter space. So we are actually touching the upper end of the model parameter space, which was not possible for any previous extragalactic FRBs like shown here. And then only other case is this galactic FRB, but our limits is only a magnitude, order of magnitude higher, or if this binospec observation is actually simultaneous, it's comparable. So we are getting to this regime and actually putting some model constraints. And then you can also compare with this with some afterglow models, like in this case, synchrotron maser model. And then here it's shown by the y-axis the external energy, and then the x-axis is the flare energy. And then these points shows the estimates from the FRB observation itself, and then the shaded region shows the constraints from the optical data. So if you assume just a constant external density distribution, you can actually rule out these models by comparing the radio burst measurements and then the optical measurements. So it's really interesting that we are actually getting into the regime that we can actually provide some model constraints from the optical observations. So I just leave my summary here and take any questions you have.
You mentioned this one is 100 bursts per hour, which means they're typically separated by 100 seconds. So that means with your exposure, you could see multiple bursts, and therefore you can get arbitrarily close to, I guess it depends on how precisely you know the shutter speed.
Yeah, so during, actually that's a really good point, and during a few exposures that we have, we actually had multiple FRBs in a single exposure. So I think 3 at the most. And then for those, we know the arriving time, but we don't know the individual flux measurements in the radio have not been public yet, so we don't know. But if those are out, we can actually put tighter constraints, because you should expect even higher luminosity in the optical if there's anything. So that way, when all of these data come public, we can actually put even tighter constraints.
Well, no, this is really great stuff. It's amazing. I never thought that you can actually do simultaneous optical and radio. But I missed the final message, the synchrotron maser model. Are you ruling it out, or are you saying some part of that model is ruled out?
Yeah, some part of the model.
Which part?
So we are talking, so here we are assuming so I mentioned about this external density distribution. So we are assuming this constant, just a flat density distribution. And then for that case, and then for high, radio fluence FRBs, we would expect optical emission that is above our optical limits. So those parameter space can be ruled out, but if this density distribution is actually more like a wind-like, then it's slightly weaker. So it also depends on the knowledge of this density distribution.
Thank you.
So I'm wondering if you tried to explore the archives, because there are dozens of telescopes around the world taking wide field and pretty deep images in random places of the sky at any moment. And one thing is that you have the 48-inch telescope here, but the other thing is that if for some reason a particular field was observed at the same time by DECAM or by, I don't know, which is more than 1 square degree, or by HSC, which is, again, a couple of square degrees, or by mega gamma CFHT. This will get to your limits by, like, I don't know, 3, 4, 5 magnitudes.
Yeah, so we looked at the public transit surveys like ZTF's Wiki Transit Facility and then also Atlas. Those we looked at.
Shallow.
Yeah, those are shallow.
No, I'm talking about like programs. Basically, if you try to explore the images which were taken in the framework of totally different programs, just, I don't know, maybe setting up a collaboration with CFHT or with Subaru or with several telescopes to make sure that if they take images to verify, and it's not related to the science of the original proposal, you could verify whether there is whether there is any counterpart for your source.
Yeah, that's an interesting point. But at least for the lessons that we learned from like ZTF and Atlas, which has much higher field coverage, we only find one simultaneous observation out of all these FRBs from ZTF. So the chances for the deeper but narrower field images likely low. Yeah.
So don't forget that the other limiting part is you need to detect the FRBs, right? And,
Yeah.
and even CHIME, first of all, is in the north, not in the south. It's only seeing a small fraction of the sky at any given time. So you have to, the level of fortuitousness here is very low.
Yeah, but I guess it doesn't have to check at least.
Any other comments? If not, let's thank Daichi.
Ready? Okay. So, thanks for coming back, staying. This morning I talked about star formation, star cluster formation, multiple populations, binary stars. It was all very exciting. It was work that 2 of my graduate students have done. The 3rd graduate student was very happy to hear I was getting another talk, so now I'm going to talk about his work. Okay. It starts in a similar place. This is a slide that I had in my morning talk. This is an image from a GMC 10 to the 7 solar masses. It collapses, it forms stars, it's got filaments, it's all cool and very exciting. And being computational, of course, we want to get to as high resolution as possible, but we can't go as far as we want. So we use sync particles. And one of the things we do with those sync particles is we call them star clusters, because we're simulators. It's a star cluster. And within that sync particle, we have stars form, we have gas. Those sync particles in this particular simulation are allowed to merge. And so we build up our most massive star cluster, which is this one here, from a number of things, from the accretion of gas onto that particular sync particle, but also from other sync particles coming closer together. This is a merger tree of that most massive cluster. This is the most massive one. These are the other guys that came along. The mass, there's 2 colors here. The darker color is stars that became part of the star cluster by forming within that original sync. And the lighter color is stars that came into the cluster as formed from, other clusters and merged. Okay? Cool. Really exciting. We learned all kinds of things. But the sync particle is a circle. And inside the circle, stuff happens. But we don't know what it is. We just tell it to form stars, and we tell it to merge, and we tell it all kinds of things. And I'm interested in the actual formation of those clusters, the details of how that works, and so I want to do this. I want to take a sync particle and put inside of it real stars. Okay, they're blue, sorry. But the size of the circle is the mass of the star. There's also gas there. You can sort of see a grayscale. So, okay, so now I have a real star cluster with real stars and real gas, and I want to merge it with another star cluster. So I go to my computer, and I get another star cluster. Cool. And I put them in a simulation box. Cool. And I merge them. Ooh, come on. Ooh, thank you. Yes. Okay, so now I know what happens when two sync particles merge because I'm following it. I have real stellar dynamics here. Proper n-body, there's softening, but not much. Proper hydrodynamics, like I'm doing it all, okay? And I'm doing it in the Muse framework. You can ask me about that later, but it's a nice framework where you can plug in different codes, have them talk to each other properly, we think, and actually, run through the simulations and see what happens. Okay, so what the sync particle prescription says is that what happens in the sync particle stays in the sync particle. Okay, once you've become a sync particle, you are a circle, and nothing can come out of the circle. Now, as you can see, nothing comes out of the oops. So we've looked at these simulations in a lot of detail to see exactly what happens. And of course, what happens in the sync particle doesn't necessarily stay in the sync particle. The simple approach is sometimes, simple, right? Sort of by definition. So what can we learn that's better from that? This is a different different simulation of something that the sync particle prescription said was a merger, but is not a merger. What happened in Las Vegas most definitely left Las Vegas, right? Okay. What we've discovered from these simulations, and this is something that my student published last year, is that we lose sometimes up to 20% of the mass in gas from these simulations. And remember, that's going to change my star formation efficiency, my total amount of star formation, the mass of my final cluster, all my GMC stuff might be slightly wrong. Okay, 20%, what's 20% between friends, but maybe this is important, okay? Also, the sync particle prescription said that when two sync particles come together, they form a single more massive cluster with the mass of stars and gas that they had before, and that's not necessarily true. Turns out that the velocity of the collision matters. Oh my goodness, who knew? But the velocity at which this happens is about 10 kilometers per second, which is not super fast, right? Like that's entirely reasonable inside a GMC. What also happens is that we can change the amount of dense gas within the sync particle by having larger or smaller things run into the sync particle. And it's the dense gas that is going to make the stars. And so if we have less dense gas than we thought we did, then we shouldn't do that anymore. Okay, so that was one of the things that the large-scale simulation told us that happened to form a star cluster. But there are two other things that happened in there as well. And of course, being good simulators, we've modeled that too. The first is that our little sync particle, now cluster with gas, is moving through the GMC. And maybe it's interacting with the GMC gas, and maybe it's not. So we're interested in that. And the other thing is that we have filaments, and the filaments are coming in to the little sync particle. And in the large-scale simulation, the gas that came in or near the sync particle went into the sync particle. But is that what's actually going to happen in these particular ones? So this is paper that has been submitted now. Good referee report should be resubmitted shortly. And what we discovered, one non-movie plot for the whole talk, is that the percentage, this is plotting the percentage of gas that was initially in the cluster, i.e. inside the sync particle that cannot come out, which now becomes unbound when you have filaments impacting this. So we tried three things. We tried single filament from one side. We tried 2 filaments, simulators, entirely 180 degrees from each other. You know, we'll work on that. And then the 3 filament one that I showed you. And so those are these lines, and you can see that we can lose 15 to 20% of the initially bound cluster gas. Okay, we're adding more gas, so the total amount of gas that comes in is still larger. But we're losing some stuff that was never supposed to be lost. We also put some of these inside a background medium and did the whole thing together and discovered that, surprise, surprise, if you have a background medium around your sink particle, this helps, but you're still, like, we're still losing 5 to 10%. Okay, it's over 3 million years and something else may have happened over that time, but it's all important. So, I'm nowhere near my time, but I think we've had a long lunch, so I'm just going to leave up my last few points and point out my students. This is the one who did this. This is the one who did, these are the ones who did the stuff this morning. So I claim, I'm biased, but I claim stellar dynamics and hydrodynamics are both important for the first 5 million years of star cluster formation. It's really messy and it's really fun. Thank you.
This comes at no surprise to people who do collisions of galaxies, because roughly the same amount of stars, dark matter, and gas are being lost in galaxy mergers. So this is very much similar phenomenology, but of course the details are different.
And I started as a stellar collisions person, and this also comes as no surprise, although I had to fight that fight 20 years ago as well. Right? 2 stars merging does not produce 1 star of the mass of the sum of the 2 stars, just putting it out there. Okay.
And the same is true for fusion, 2 hydrogen.
Exactly.
Anyway.
It's not quite the same physics.
Not the same physics.
Yes.
Go ahead.
I missed the first talk, so I'm not sure if you mentioned this before, but do you include any feedback in your simulations?
In these ones, no. In the larger scale, yes. And in the stuff I talked about this morning, yes. So, yeah.
Yes, please, up there.
Up here. Hi. So if you have a thermal background of, say, dark subhalos at the same scale, does it help or does it interfere with retaining mass?
These are like a parsec.
Yeah. And so we have these, in stellar streams, for example, people think that parsec scale subhalos are zipping around, disrupting it. Yeah.
This is true. I would think the hydro would be more important, but I'm biased that way.
Question?
Yep.
Please.
Fleur?
Yeah, so when in the last plot, like the line goes down, is that like material from the surrounding coming in, or is that just like it's different simulations on different time scales?
Going up and coming down?
Yeah.
Again. So this is, we're only tracing the gas mass that was once in the cluster. What happens is that the filaments start impacting, and there's a bit of a, I'm going to say shock, but I don't necessarily mean shock. There's a sudden change in what's going on, and then the whole system settles a little bit. So that's the, the first impact of the filament, and then some change. Yeah.
Yes, please.
How large is the net effect on like things like cluster mass function or something like this? So should we believe like any of this?
He's not finished his PhD yet. We'll get back to him.
He will not finish the PhD until he answers this.
Oh, I'll let him know you said it.
Please.
Yes.
I'm slightly confused on this plot. Okay, so what is the red line?
So the red line is the 3 filament case that I showed you. And the other gray ones are either 1 filament or 2 filaments. We only did 1 3 filament case because I wanted the PhD to graduate. And, I mean, how many parameters do you have? Different masses and different angles and so on. He was only allowed 1 3 filament case, which he took from observation. So that was a good
Thank you so much, Alison. We learned a lot from you today.